Yeah, hello everyone. So my name is Tran, or Kimberly Tran. And I've been working with Git for like a long time now. I think I first ran into Git back in 2007 or so, and I've worked with Git in several organizations, introduced people to Git. So I'm kind of familiar with the difficulties that newer teams may have with adopting Git. So this is my attempt at a sort of Git tutorial that is not like most tutorials you see out there. So this tutorial, or this introduction to Git, is around the idea of approaching Git at its most native, which is a graph-first approach. So Git is best understood as a system for manipulating graphs. So what does your graph look like? And then what do you want your graph to morph into? What do you want your graph to look like? And then what are the commands you should apply to get between those two graphs? So that's why I'm calling this sort of the graph-first approach. You approach Git not from the command basis or the state of your code, but from the native elements of Git itself, which are the commits. Okay. So I have like 25 slides, so I'm going to try to go through them fairly quick, but also pause at certain slides just for questions. So the general outline of this presentation is we're going to go through some basic Git fundamentals to set the stage, and then I'll start throwing graphs at you all and show common use cases and how those graphs should be morphed. So you're going to see a lot of graphs in this presentation. Okay. So the typical introduction to Git is for a team that comes from a traditional non-distributed version control system. So these are the systems that I can recollect working with in my career. So Perforce, ClearCase, CVS, Fisher Source Safe. And they're all very different from Git. They're not a distributed system. They're a central repository, and so the terminologies and the way they work fundamentally is different. Also, these systems don't have a clear model of how they work. For instance, when we were using CVS, we actually had the consensus smartest guy in the room, typical MIT dropout, who was the CVS maintainer. Every once in a while, CVS would mess up, and then he would go into the CVS repository, the database itself, make some like weird commands, and then straighten things out. And no one knew how CVS actually worked. Git is not like that. Git has a really nice, clean model of how it works, and you can manipulate Git using that model 100% reliably. Understand the model, you understand Git. Okay. Yeah. So usually you come from these traditional systems. You're interested in Git commands, and you try to map Git commands to traditional version control systems. That doesn't work very well because Git has its own notion, own models that is inherent to its structure and doesn't map very well to traditional version control systems. And the problem is compounded by the fact that the commands in Git may look the same. For instance, you have a checkout and a commit, but they do very different things in Git, and that's one of the sources of difficulty. So that usually confusion arises, and people just don't know what Git did to their code. Okay, so we're going to start out with the fundamentals of Git. Okay, so these are the basic elements of Git and the foundation of Git. Git consists of commits, which is the commit graph that we're going to talk about. It's a database for your source code. And then there's the working directory, the index and the staging area, the mysterious index or staging area, which you'll see in the Git documentation. And then what I'm calling metadata, which is branches, tags, and remotes. It's data about the repository itself. Okay, so it's very interesting that branches, tags, and remotes are actually metadata. I don't consider those things like intrinsic to the Git model. They're actually an overlay onto commits, working area, and the index staging area. Okay, and that part of it will be very key once we'll talk more about what this metadata does. Okay, so we're going to go through these one by one. So commits. So Git is a database of your code, and just instantly, the database is in that hidden Git directory in your repo root. Okay. The smallest unit of change is a commit. And you can think of commit then as like a transaction in a regular database, where the transaction or your change to your code base. So here's an example of 3 changes over time. The arrow of time in this presentation always goes from left to right, and the commits are laid down and ordered. You have your first commit A, and then sometimes later you make another commit B that is based on A, and then later on you create C. I think you've all probably seen this type of graph before. Okay, and though this is the model of how Git represents commits, it's also a very good working model in the sense that the state of your code at any commit is determined by replaying all the commits that came before it. So to get to your code at C, you traverse the graph, finding all of A, B, and whatever, and then you replay them one by one. And that's almost exactly how Git works in terms of like getting your working directory to some commit state. Now, it has a ton of like caching and fancy programs to make it like lightning speed, but essentially that's how it works. You always start from like the very first set of primordial commits, and you replay the commit graph until you get to some commit. Okay. Any questions about commits here that I can take real quickly, based on this understanding of what a commit is? Okay, so I'm going to just keep on going through these slides. Okay, so next up is the commit graph. So we already saw this simple commit graph of A, B, and C, but there's also more complex commit graphs where B can have 2 parents. So a commit always has some parents, one or more parents, except for the very first commits, which don't have any parents. So this is, you've also heard the term directed acyclic graph. And what that means is that this graph, there are no cycles in this graph. So you can traverse from C, and you may see a node more than once because it's a graph, but you'll never get back to C itself. So from C, you can always get a deterministic set of nodes that were used to get to C itself. Okay, and commits have a uniqueness guarantees and are tamper-proof in the sense that each of these commits has a hash, and then that hash is actually propagated to the hash of the new commit. It's part of the new commit, so that it's tamper-proof. So every commit is unique, and you cannot tamper with that commit hash without other people detecting it. Okay, so they're like GUIDs in that respect, and that's very powerful in the sense of, if you want to pass commits around, you can just refer to their commit hash, and every single commit hash in the world across every repository in the world is unique. Okay. So you have a commit graph, which is the database of your code, but you can't work with that code until it's expressed in some sort of writable format, and that's your working directory. So the working directory is the editable state of your code. It's always relative to some commit. It's just the file system. So the file system mirrors the state of your commit, and then it's also relative to an optional branch. So that's actually key there, because your working directory is almost always attached to a commit, but because the branch is optional, sometimes you may be off in what is known as you might have seen it already, detached head state, which means that you're on a commit that has no branch. So you can work on it, and it behaves just like working on a branch, except you can't refer back to that branch again via a branch tag. So the idea here is that it's the commit that is important, and the branch, being metadata, is not so important. That's what I wanted to get across here. Okay, so orient yourself to the commit and not necessarily the branch. You have to be aware of the branch, but just be aware that that branch is metadata. Okay. All right, so now we get to the index staging area. So we have like your commit graph, which is like the current state, A, B, and C. Now we want to make a change to this commit graph. So anytime you want to make a change, there's going to be a commit to B, right? So this D prime is the commit to B. And that's exactly what the staging area is. It's the commit that Git is building as you are working with your code. It's a commit to B. And changes have to be explicitly added to D from the working directory. That's why you have the git add separation from the commit, right? You can actually do a commit, and if you can add anything, the D prime, the staging area, the commit to B is empty, and you get nothing. And so they call it the index staging area, but I like to think of it as the commit to B. The only difference between D prime and D itself, once it's committed, is that it becomes unmodifiable. It gets locked in stone once you commit the changes. And this is actually why git commit is a constant time operation. And you can actually test it out by yourself by just say like, cloning the Linux source code repository, deleting the git repo, and then re-adding everything, and then you can find that git commit happens instantaneously, no matter how many files you have, because all it's doing, the commit is already built, and all it's doing is flipping a bit to make that a commit that's no longer editable. So that's the staging area. Okay. Any questions about the staging area? I know that can be a foreign concept to a lot of people because it's not a concept that's in other source code control systems. Okay, I'll keep going. Okay, so we get to the last bit of the Git fundamentals, which is the metadata. So Git is, you hear that Git is append only, and that's not entirely true because only the commit graph is append only. You could add to the graph, but you can't modify the existing graph and change the links between two existing commits. Right? It's not allowed. You can only add to the commit graph. But everything else is fair game. The tags, the branches, general bookkeeping, like things like remotes, and what branches map to what branches, that is all just metadata. And furthermore, that metadata is actually contained in a text file within the .git repo. It's a config file. You can actually look in there. If you do things like adding a branch, you'll look at that file and you'll see the new entry has been added to that file so that Git can know what branch is tracking which commit basically, or which branch is tracking some remote commit for you to push and pull easily. Okay, so that's a kind of a key concept that yes, Git is append only, but only for commit graphs. And what you're manipulating really is the metadata around what these branches and tags point to. Okay, so that's just a quick, just very fast overview of Git fundamentals. But I will also hold that that's all you need to actually work with Git, is to understand that's the essential Git model. And everything else is just syntactic sugar or commands added to Git to make it easier to work with. Mostly because commits, you can't remember commit hashes, right? Humans have to attach like symbolic labels to commit hashes to allow them to work. So almost all of Git, a lot of Git is around this metadata system, to keeping track of which branches point where. Okay. Okay, so more notes on the append only. Since the graph can only be added to, this implies that it's the metadata that is changing. So furthermore, that implies that a push, for instance, you do a git push, what you're doing is changing what commit the branch is pointing at. You're not changing the graph itself. You're changing the branch. There's a symbolic tag out there. There's a symbolic slot for this branch, and it has a pointer to the commit, and you're pointing it to some new commit. So when you push, the old commit is always still there because it gives append only. So if you know the commit hash, its numeric hash, you can always get back to it. So this leads to what I'm calling the push rule. So when you push a branch, the branch can only be pushed if no commits are lost. And what that means is if you modify the branch to point to new commit, that new branch, you must be able to access the old commit from that new branch. If you can't, then that commit is lost, right? So that's sometimes when you push, it will refuse to push because doing so would cause essentially data loss. Commits will not really be reachable. Okay, so that's a sort of a key idea behind this presentation, this push rule. Okay. Questions? Okay, I'm going to assume no. We'll go on to the push rule in action. So there are a number of cases. So there's 3 cases. The push rule, you can accept, reject, or force. So this is the accept case. Okay. So this is the state of the remote repository, ABC. Here is a newly pushed commit, D, and you want origin developed, point to D without losing data. Can you do this? Yes, because when you do this, C is still accessible, so therefore the commit is accepted. So the graph, so by the push rule, the branches can move to a new commit hash deterministically without losing data, meaning the old branch is still reachable. The old commit is still reachable from the new commit. Okay, so this is the normal happy path when you push something to the foreign repository. Okay. So the other case is the reject case. So this is a more complex diagram. Okay, so here is the remote repository. So basically, you were at B, someone else pushed C, and you push B, B, and D. Okay. So when you try to push this, and you want this shape here, you want your shape to take precedent, right? You want to push this up there. If you do it and set origin develop to D, C is lost because it's no longer traversable from D itself. You can go to BB and B and A, but you can't to C. These are directed graphs. Right? There's no pointer from B to C at all. So you can't reverse this. So therefore, this is rejected. And that's why when you push something like this, Git will say you have to. The foreign remote repository has changed, and it rejects your new commit. Okay. Another key idea is that this push rule applies to every single branch. There's nothing special about the master or the develop branch. It applies to branch that you create even. So you have a private branch and it gets in this state, perhaps because if you've done like rewrite your branches locally and you try to push, you'll also get this newly pushed commit is rejected. So it's a generic mechanism. There's nothing special about those other branches. Okay. So the last case is the force. So this is like this exact previous diagram. But you want this now to, so this B here is like the common commit that you both started from. Someone else pushed C, you've pushed B, B, and D, and now you want your branch to look like this. C is lost, it's only reachable, but you can force Git to actually do this by setting the force command, by setting the force parameter on the push. What you do then is that you're saying that, no, just move this origin develop branch to D, and you don't care that C is lost. And so this is why you don't want this to be done on a shared branch, because once the C is lost, that causes problems to other people who may have C in their Git repository, and they would need to then recover from that. Okay. So when I say C is lost here, it's gone, but it's not really, because remember, the commit graph is append only. So this C here is still pointing to B and A. You still have this original branch sitting out there. It's just not accessible. But if you know the commit hash of C, you could always get right back to it. Okay. But there's a small window because eventually C will be garbage collected. Any node that Git can't reach via a branch or a tag is eventually garbage collected. But you have like some, I mean, generally they don't garbage collect instantaneously. So you can always recover if you know C. And there are tools also for like trying to find C when there is no way to traverse to it. So there are tools that will pick up these like sort of orphan nodes. So you can recover from something like this if you do it inadvertently. And it's almost very likely that C is also in some other, one of your colleagues' repository if they haven't pulled yet. So you can also recover that way too, right? So nothing much is ever lost with Git because it's append only, which is one of the ways that you can actually work with, Git confidently and reliably, because you know that the commit graph is append only. Okay. Okay, so we've talked a little bit about pushing changes. Okay, so if the local repository is in this shape, this is your local develop branch, and the remote repository is in this shape, it's one commit behind, it's A and B, and you want the remote repository in this shape. You want develop and origin develop to point to the same thing. And this notation here is actually on purpose in the sense that a branch is just metadata on this commit node. When you create a branch in Git, you're not laying down new commits or anything. You're just adding metadata that says that develop points to this branch, or origin develop points to this branch, or maybe some new branch that you created also points to C. You're creating metadata that points to your commit graph. You're not creating new graphs at all. Okay. So you can make the remote repository the same shape as my graph. And once you do this, you push your change. Now it's A, B, and C, and develop and origin develop point to the same thing. So you were at this shape, the repo is in this shape, and this is the shape that you want to get to. And the way you get there is you can just push your changes. And this works because by the push rule, B is still reachable from C. So that's a push that does not lose history. Okay. Now, if you are making concurrent changes, there's two ways to deal with this. This is the rebase case, right? So if your local repository is A and B, and the remote repository is A and C, so if you both started from A, you put down B, and someone else has put down C. Okay, so to actually get your changes up to the repository, you want your local repository to look like this. You want to replay B on top of A and C. And so that's exactly what rebase does. Rebase will take your change B here and then play it back on C to produce A, C, and B. And once it's in this shape, it cannot be pushed because by the push rule, C is still accessible. And so that's how concurrent changes work in the rebase workflow. The other workflow that you may be working with uses merge. So the same situation as before. You have A, B, and AC. And you want your repository to look at this shape instead. So here's A and B. Here is your original branch. Here's AC. This is what came in from the remote branch. And then D is the merge. And this is what happens if you do a git pull. So if you're at AB and you pull AC, what git does is that it first brings down AC and then it does a merge. So a git pull, I'm sure you've seen this before, is git pull is a combination of a git fetch, meaning fetch will bring down AC, and then merge will then combine AC and AB here into this new commit D. And then now both develop and origin develop will point to D. And now you can push this. Okay. Now you can push it now because by the push rule, C here, which is the original commit, is still accessible from D. So Git will allow this push. However, if you think about like if you have a big team and everyone is using the merge workflow, you can see that there are all these these nonlinear merge paths, and if you have multiple of them, your Git commit graph can look really hairy because there's too many, there's a ton of branches. So this workflow is generally not recommended for larger teams because of the large number of nonlinear merges happening. Any questions about these changes, these ways of merging and rebasing changes?
There was a question earlier about rebasing, but I believe it got answered. So
okay.
I think that
I'm sorry. I'm only seeing my. I'm a rather new presenter, so I only see my presentation. I don't see any interaction from other people. Should I try to?
Yeah, no worries, no worries. Yeah, it was just VJ was asking a few slides back if basically is that the case where you may be asked to rebase, and then 2 slides after that you covered rebase. So I think you've answered his question. If not, VJ, please feel free to chime in.
Yeah, no, all set. I think that was a question. I've seen that warning sometimes when I'm trying to pull from the remote, because the remote has advanced in one way and the local has advanced in a different way.
Yes. Yeah. So this here, when you do this pull here, the other note I wanted to make was that make sure that you update your Git Git executable to be the very close to the newest version. I should have checked before this presentation, but Git is actually, they continue to refine it. For instance, they've created a new switch for Git pull, which is fast forward only. So it actually prevents you from pulling and creating this D automatically. So it will only pull if it can produce a linear history. So I highly recommend you turn on that fast forward only for Git pull so that you don't get into this case. Okay, so it'll force you to basically always use the rebase workflow instead of these merge cycles. Okay,
We've got another question, Kim. From Pavan. How does git stash work in this case of merge? Does it simply delete the change as it is not yet committed to the local branch?
Git stash, they're asking?
Yeah, stash.
Okay, so you do a git stash, you're stashing the index. So if you go back to the index is the commit to B, right? So during the merge, if you haven't committed the index yet, the stash, you're stashing the commit to B would actually be this D prime here. So once you stash this, you are back to just AB because AC hasn't been incorporated. So once you stash D prime, if that's the index area, then you're back to this AB here. And I'll cover stash a little bit too, actually. So hopefully that'll answer their question.
Cool. That's it so far.
Okay. Yeah, so stash basically undoes D and leave your repository at AB. You haven't lost anything. It's just you've lost the merge that Git wanted to do for you, which may or may not be relevant to your use case. Okay.
We just got another question.
Uh-huh.
So John has a question. So generally speaking, in larger teams, you are better off rebasing your branch and replaying your changes rather than doing a merge.
Yes, and if you're using VSTS, Microsoft or Azure, is that what it's called now? I can't keep track what they keep calling it, but basically the Azure Azure DevOps, basically. Yeah, if you use the pull request mechanism for making code changes, so basically you would lock down your develop branch, and you allow no one to push changes directly to the develop branch. All changes must be pushed as a feature branch, and you must issue a pull request. And then furthermore, after you do that, they've just recently in the last 6 months added a refinement where the only pull request options you have are rebase, squash, or fast forward, basically. They'll only allow you to do rebases, and they won't allow you to actually do a merge anymore. And once you turn that on, you would get very linear Git commit histories, which are very much easier to look at. Plus, you have almost like absolute safety because no one is pushing anything directly to your develop branch. And awesome. So you basically you want to use the rebase workflow, but I would say only if you have something like VSTS where you can use the pull request mechanism, because that makes it completely safe. Okay. Hopefully that answers John's question.
Yeah, I think you did.
Okay. So now we get to races. Okay, so because if you're on a large team, the repo during peak hours, the repo could be changing a lot, and when you end of the day, as you're pushing changes, you may find that people are beating you to pushing your changes, so that by the time you push, you're already out of date. So what happens is your local repo is in this shape. So you all start at A, and you've now laid down B. And that's your local repository. The remote repository is now in AC. Someone else started A, and they beat you to the punch and pushed AC. Okay. So now to push your changes, you have to get your repo into this state, because B can reach C. So therefore, Git will allow this by the push rule. Git will allow this push. Right. So what you do is you rebase your changes AB onto AC, and what Git does in rebase is that it notices that you're both started at A, so it'll take B, and it'll replay it onto AC, and it'll produce AC and B. So that's fairly basic. Okay, so now you want to push it, but before you could push, because this is distributed, so other people could have beat you to the punch again. So before you push ACB, the remote repo has changed again, and someone else has sneaked in D now. So the repo now is at ACD, so you can't push. So Git will say, well, if I push AC and B, D is no longer reachable from B, so therefore by the push rule, it's rejected. Okay, so to push successfully, you have to do the same thing again. You have to fetch, and you have to rebase AC and B onto AC and D. And the same rebase mechanism works because they notice that you are both starting at C. B is the only difference. So you take B and you replay into AC and D, and you produce AC, D, and B. And this particular commit graph can be successfully pushed because D is reachable from B. Now you can push. Okay. So the basic strategy here is to just keep on fetching and rebasing until you can actually beat someone else to the punch and push up your changes. And this is much easier done if B is your only change. And so if you are working with Git and you are following the rule of, commit early and often, which I always do, right? Because once you commit something, you can always roll back to it. So I tend to commit early and often, and I even tend to push my changes onto the remote code base, the remote repository under my own branch. So when time for me to end of the day when I'm pushing my changes, I may have like 5 or 6 commit here. I may have B, C, D, and E. But if I'm trying to, do the rebase into other people's code, it's much easier if everything is collapsed down into B. And that's easily done also, and I can also, I'll cover some of that too. So this is why this particular slide only works with one commit, because that's the state you want your local develop branch to be in before you actually push. Okay, so that's just a hint on how to easier work with Git at the end of the day when you're trying to push your changes. Any questions about resolving races here? Because this can happen pretty often in larger teams, and it could cause a lot of confusion when your changes can't be commit. Also, this slide is also embracing the idea of rebase too, because there's so many presentations out there, so many tutorials out there say to stay away from rebase unless you know what you're doing. But if you understand that the commit graph can only be appended to, and you understand the push rule, rebase is completely safe, and it's really hard to lose data in Git anyway. Okay, so I'm encouraging people to actually use rebase instead of merging. And with some of these rules in this presentation, you should be able to work out what is a safe rebase and what's not. And that's actually really important too. But so I'm hopeful that this presentation will give you the tools to actually make that judgment about what is a safe rebase or not. Okay. Okay. So all right. So time checked. Shoot, it's 12:42. I'm only halfway through my presentation. This is actually not good. Resetting branches. So you can move around the commit graph at will. So there's a huge commit graph. The current branch moves to the target commit. That's the key thing here. The current branch and your working directory moves. You're moving the current branch. You're not moving the commit graph at all. You're moving the branch. So if the current shape is like this, A, B, C, and D, and you want to rewind your local branch to be here for some reason, you can do that, right? You can actually do git reset, which is the same thing as move branch. You can say you're on the develop branch, and now you want the develop branch to point to B instead. So this is what the shape that you want, right? And so you can do that, but other questions arise though. What happens to C and D when you do this? And that's where Git gives you a choice. If you do a git reset hard, then C and D are lost on the current branch. They don't appear at all. It's exactly like your branch at B, and C and D are just off back on origin develop, and you can then diverge from this point on. Okay, or you can actually have C and D stay in the working directory as changed files, and that's when you do the git reset soft. And you do that back to B here, the change to C and D here shows up as just changed files. You do git status, you'll see these changed files. They're not added to the index though, so they're just unadded. And there's another mode called mix that will actually add it to the index. Okay, but I'm not going to cover that. Okay, so this is really key, because this is a really easy way for you then to squash changes. Right, so if you have C and D, let's say B is where you diverge, right? You're at B, you've done a ton of work, C, D, and E, let's say C and D, and you want to collapse them all. You can do that via the reset command instead of the more harder to understand rebase squash commands. Okay, so you can do a git reset hard or soft here, and then instead of the work in progress rebase squashing. So here, if you are, this is your current commit graph, C and D are work in progress, and you don't want such commits to cut up the graph because it's just working in progress. So you want your graph to look like this instead. A, B, and C and D are combined into one commit. So you have 3 commits instead of 4. To get there, you do a reset soft. So this is the state you want. This is your current state of the graph. This is the graph you want to get to. To do that, you do a reset soft, producing A, B, with C and D now as change files in your working directory. So now your develop points point to B. Now you can add those files to the index staging area. You produce the CD prime, which is the staging area, and now you commit it. Now you have A, B, and CD. That is just 3 commits instead of 4. Okay, so you can do this for any number of commits out here, right? You can have like 10 commits to the right here. If you select back to B, you can combine them all in just one fell swoop. That's a very simple way to squash your changes instead of using rebase. Questions real quick? I'm going to try just quickening the pace here a little bit.
Yep, no questions.
Okay. Okay. Here's another case where you work on the wrong branch. This is fairly typical, right? So the remote branch looks like this. You have a change A and B. Your local branch is you accidentally checked in C to your local develop branch, right? So you've committed and looks like A, B, and C. Instead, what you want your repo to be in this shape, where A, B, and C is your feature branch, and A and B is your develop branch. Okay, so you could just create a branch called feature, and now both your develop branch and feature point to A, B, and C. This is a git create branch command. And now you can switch the develop branch and then reset hard back to B, leaving your graph in the desired shape, right? So this is your repo when it looks like this, and these commands now have your repo looking like the shape you want. Does that make sense? What I just went through there?
It does to me. I've done that many times.
Okay, good. Yeah. So you've visualized the graph intuitively and using reset to get your branches back to the way that you want them to be. Okay. Another way to work on the wrong branch and fix that is using a stash. So it's a little more work, but it has some advantages of staying on the same branch. So the basic setup is still the same. Okay, but what you do is you're on the develop branch, and what you can do is you can reset soft to B. So now develop is pointing to B and leaving your changes in the working directory. Now you can stash the what's in the staging area, so you have this. You add the changes to the staging area, producing the C prime here, which is the staging area, and now you can stash C. If you stash it, you run git stash now. All it does is it takes C here, which is the commit to B, and puts it into the stash. So it's a hint here. The stash is just a commit, actually. It's a stash and the index areas are mostly the same thing. It just commits to B. Git does a lot of that in its architecture and in the way it's designed, where it's reusing commits up for almost everything. Okay. So once you stash C prime here, your develop branch is back to exactly what you were looking for. And now you can just create your feature branch. And you can pop the feature branch off from the stash, leaving C. Now you pop the feature branch and then commit it, and now you have A, B, and C, which is your feature branch, and A, B is back to develop, which is exactly the shape that you were desiring, right? So that is, I keep on, I'm sorry, I need to stop using my mouse pad to do this because I'm changing the presentation too much. Yeah, here's where I was. Okay, so this is another approach to the working on the wrong branch, but using stash instead. Many ways to do the same operation in Git. Okay. So another thing that that I use a lot, which maybe other people aren't using, is that you have persistent feature and bug branches. And the advantage of doing that is that you never or rarely create another branch. So you don't have a lot of branch to keep track of. So what this does is you have just a small number of branches. So what I do is I have a feature branch and a bug branch, because I usually don't have the bandwidth to work on more than one feature and one bug at a time. Okay. So instead of creating new branches, if the shape of the current repo is A, B, and C, and the shape of the local repo, so this is the remote repo, A, B, and C are the changes up there. The local repo has A and B only, and A, B, and D is my feature branch. Okay. In this case, the Kim feature branch represents work that's already merged, so I don't care about A, B, and D anymore. So, but I stay in this branch, and what I want my graph to look like is I want my graph to look like this. When I start on my new feature, I want A, B, and C to be pointed at by both origin develop, but also my Kim feature branch. Okay, so if I'm this state right here, if I do a fetch, what I have is this state, right, where I have the original origin develop. I have my Kim feature. So all this does is advance A, B, into C. And now I can just move the feature branch with the git reset hard to origin develop, leaving exactly the state where I want to be when I'm starting a new feature. But that is, my Kim feature branch is concurrent with the origin develop branch. And you can keep doing this for each feature cycle, where you work on one feature, after you push it and issue the pull release, you can start off the next time you can reuse the same branch, and you reuse the same branch also for the bugs. So this is another way of working with Git a little more efficiently. Okay. All right, so yeah, getting close to the end here. Okay, so those are some of the use cases that I wanted to highlight with with the commit graph. Okay, so we come next to the idea. This is a really super powerful idea that because commits are universal, every single commit is uniquely identified, and because the commit also has its history, it points to its parents. It's the entire history. Okay. So every commit hash, every created, shares the same logical, universe-spanning repository. Okay, that may sound grand, but it's true. So my view of Git is that your local repository, or any repository, is just a subset of this universal repository. So taking the logical extreme, your code is in the same logical repository as Microsoft's code for Windows, if they share the same sort of Git basic infrastructure of commit hashes. Just at the repos, you have different slices of this universal repo. And so furthermore, you can move any commit into your own repository, and you could push your commit into any repository, given the push, allowing for the push rule and all that. Okay. So once you do this, because the commit is also its history graph, you've moved the entire quote-unquote branch. So you've slinging commits around. And so how do you add commits from arbitrary remote to your own local repository? That's where the metadata come in, and that's where remotes come in. So we don't have time to cover remotes at all, but remotes are just pointers to another repository. Once you add a remote, and that's the git remote command, once you add a remote, you can fetch that remote into your local repository, and then you have the branches from that repository in your own, and you can then check those branches out and work on them. Okay, so this is also security around this too, so you must be allowed to do this. But at its core, Git allows you to move any arbitrary commit into your own repository. Okay. Any questions on remotes I can answer quickly at all? Okay. Okay, so in summary, Git commands are graph manipulation commands. They're best understood as ways to manipulate your graph. And then because graphs are append only, what you're really changing is the metadata points to these commits. You're not modifying the graphs themselves in the sense you're doing surgery in the graph. I guess that's completely disallowed. You cannot change a commits parent. You're only adding to those graphs, and you're changing the metadata, the branches and tags and remotes and so forth, to point to the commits that you want them to change. And Git has rules, like the push rule, to make changes to the metadata deterministic. Okay, so once you understand that, then I think it should be much easier to work with the Git commands and not get into trouble. Okay, so that actually ends my presentation. So I can have like 5 minutes or so that I can take calls if people take questions if people have specific questions that they want answered.
There's a couple. John, do you have a mic? Do you want to come off of mute and just ask your question? If not, I can read it.
Sure. Hopefully you can hear me.
Yep.
Okay, great. Yeah, I was asking if you recommend when you're creating your branches for things, do you recommend doing a local first creation and then a push to remote versus a remote first creation and a pull to then do your work?
So the way I work is I create the local branch first, and then I push. And I don't tend to push the branches until I have my first commit. But then after I first have my first commit into a local branch, then I push as often as possible, because that basically puts another copy of my code on a remote machine that I can get back to if I happen to mess up my local repository or change my code in a way that I didn't want to be changed. Yeah, so yeah, I would create the local branch first and then push it. It's just easier that way. Especially if it's your own private branch too that no one else sees.
Thank you.
Yep. And Gary's asking if we can get a copy of your slides.
Yes, I will definitely clean the slides up a little bit, create a PDF, and I'll give that to Jason, and he'll push those slides up there.
Actually, it's beyond just what you presented, but also some of the material that you were not able to present.
Okay, that'd be great. Sure, I will, yes.
Thanks.
Lots of great sessions, nice sessions. Thank you. Here's one. Have you set up local Git repos?
Yeah, and so a local Git repo is just a Git init, right? So every single project that you start can have source code control, because the Git repo is just a hidden directory inside your root directory. So a local repository is just a Git init command. You can turn a directory into a repository. And I've actually abused Git to use as a way to transfer files to remote machines, right? So you create a Git repo, you add your files to it, you push it to some central location, and then on your foreign machine, you pull that image, and now you've transferred X number of files to your new system. Does that answer your question? So a Git repo is nothing more than just a local database in your source code directory. And that's, you want to look at the git init command. So feel free to reach out to me on Twitter or via email. I think my contact information is on the meetup itself, and I would be happy to answer any questions you have on Git. Or if you reach some sort of conundrum with Git and want to reach out to me, that's perfectly fine too. I am more than happy to help people with their Git issues.
Awesome. Great. I don't see any more questions. And Olga posted your Twitter handle, so it's in the comments too. So we're good there. And Steve says a great session. Thanks, Kim.
Yeah, thank you. Thanks for attending. Hopefully that'll give you all some further insights into Git and made it less mysterious.
Awesome, great. I will once I stop the recording, it's usually like 15 minutes before I get it posted up onto YouTube, and I'll share the link in the meetup comments, and then I'll also send it to Kim so she can share it with whoever she wants to.
Okay. All right.
Great.
Thank you, everyone.
Thanks, everybody.
Thank you.
Thanks for coming.
Bye, guys.